Greetings, ChemTubi. It's kind of crazy to think that we're already on chapter 16. Not that many chapters to go in the book. You guys are doing great. So let's go ahead and jump into it. We are now doing chapter 16, Thermodynamics. So there's 4 sections to this chapter: spontaneity, entropy, the second and third laws of thermodynamics, and free energy. So our first picture here showing a geyser. And these are really cool displays of thermodynamic principles. Water inside the earth heats up, and then it rises through these small channels. You get that pressure, and it turns to steam with the water. With that pressure, gets higher and higher and higher till the water becomes steam, and then it's pushed out through a small hole at the surface. So this is at Yellowstone, someplace I want to go in my life, which hopefully, I don't know, maybe in the next few years I'll get to go. So let's go ahead and get started with 16.1, spontaneity. Something that most of us want in a relationship. But when you're like me and you've been in one for 5 years now, there's not much of that left. But that's okay, because it's all love anyway, right? Alright, so in this section, we're going to distinguish between spontaneous and non-spontaneous processes and describe the dispersal of matter and energy that accompanies certain spontaneous processes. So, what we first need to ask is, will a reaction occur naturally at a given temperature and pressure without the exertion of any outside force? So, if I take a piece of wood and I just set it on the ground, will it catch on fire by itself at the current temperature and atmospheric pressure? No, right? It's not spontaneous. But a reaction that does occur naturally under a specific set of conditions is called a spontaneous process. For instance, if I take an ice cube out of the freezer and I set it on the counter, it's going to start melting because it's at the right temperature, the right pressure. It's just spontaneously going to melt. I don't have to do anything to that ice cube to make it melt. However, if I take some water and I pour it on the counter, it's not going to spontaneously turn into an ice cube, right? We need some type of process to take energy out of it so that those water molecules slow down in their movement and then eventually come to form a solid. So if the process does not occur naturally under a specific set of conditions, it is non-spontaneous. So spontaneous process is like that first relationship, those first couple dates that you go on where it's like, hey, this is our first date. We're going to get along great. Let's, I don't know, go to the park now after we're done with our coffee. Non-spontaneous is that long-term relationship, everything's great, and generally our Friday nights are sitting on the couch watching Jeopardy and Wheel of Fortune. Not that I'm complaining, it's a great life. So again, a spontaneous process will just happen. These occur naturally with a given set of conditions without outside forces. So one example is hydrogen and oxygen will react in the presence of a spark. So when you have hydrogen, oxygen, and a spark, they are going to react to form gaseous water. So those are the conditions for this spontaneous reaction to occur. Now, the opposite reaction is going to be a non-spontaneous process. So water is not going to just spontaneously split apart into hydrogen and oxygen. You have to put something, some external force to get it to split up. So that would be like the process of electrolysis. Now, do not confuse spontaneous with fast. The rate of a reaction and spontaneity are not necessarily connected. Okay, so for instance, copper turning green and getting that patina on it. When you have a brand new copper penny, it stays pretty shiny for a long time. It doesn't just suddenly turn green, or, it doesn't just start turning green right away. It takes a lot of time. Okay, but it's still a spontaneous process. It's still reacting with oxygen to oxidize. But it's not necessarily happening fast. So here's an example. This is looking at radioactive decay of uranium-238 and technetium-99. Both of these undergo spontaneous radioactive decay, but really different rates. So the technetium, which is the blue line, decays rapidly, as you can see on our chart here. For some reason my pen's being weird. There we go. So after a day, it's already way declined. But the uranium, it looks like it's all still there, when in reality it is spontaneously decaying, just at a very, very slow pace. It has a very high half-life. Another example is diamond. So you know there's the saying, diamonds are forever? Well, guess what? They actually are not. So diamond is an allotrope of carbon. It is one of its forms. But it actually spontaneously is a spontaneous process for it to change to the graphite allotrope, which is a more stable allotrope of carbon. So technically, diamonds are not forever. So if he gives you, a diamond ring and says this, my love for you will last as long as this diamond, it's forever, it's a lie. I swear to God, I'm not soured on love. Valentine's just passed, and even though Jeff had to be with his mom, he had to drive her and stuff, and so I was alone on Valentine's Day. I had my cats, but still, I'm not sour on it, I swear. But nonetheless, diamonds do last a very, very long time. That process, like I said, spontaneity and rate are not they're not necessarily connected. So while it is a spontaneous process for diamond to turn to graphite, it takes a long time. It may as well be forever, but it technically isn't. So, if you want to be that person at a party and you hear someone say diamonds are forever, now you can throw it in their face. Okay, so like I was talking about with hydrogen and oxygen combining to form water, it's a spontaneous reaction in one direction. The other direction, the reverse direction of the reaction, is going to be non-spontaneous. So these reactions are still possible, but you just have to have a continual input of energy. So it's not like with hydrogen and oxygen with a spark that makes the reaction happen. Okay, that gets the reaction going. Whereas for water, it's not just one little bit of electrolysis makes it split apart. You have to continuously be using electricity to separate hydrogen and oxygen gas from water. So that it is a non-spontaneous process. It needs a continual input of energy. Now, many spontaneous processes are going to proceed with a decrease in energy. So they're going to a more stable configuration. So this kind of goes hand in hand with exothermic reactions, which proceed with a decrease in energy. So if you remember, exothermic reactions release energy. So spontaneous reactions are often exothermic, but not always. So just because it's exothermic does not mean it is spontaneous and vice versa, but there's a good chance that they do go together. So again, showing our water, oxygen, and a spark. All right, so there are some exceptions. So for instance, looking at solid water going to liquid water, notice it has a delta H of positive 6.01 kilojoules per mole. This means that energy has to be absorbed. Okay, it's not releasing energy, but this is spontaneous, right? At room temperature, that ice cube is going to melt. Okay, and then liquid water going to solid water, even though it's a negative enthalpy, it's still non-spontaneous. Okay, I can't have a glass of water just randomly become solid water at room temperature. I mean, it would be really freaking cool if it happened. Can you imagine, like, the money that could make you if you figured out a way to make it happen? But it won't work. So let's talk a little bit more about the spontaneity. If I have two containers, I have these two gas containers and they have the seal in between them. When I open this valve, the gas that's in one side is going to spontaneously expand to fill both containers. So we have one side that's filled and one that's empty until we open up the stopcock. So this is a spontaneous process, but there's no change in energy. The gas is just moving. Okay. So you could even, when you're looking at this, you could even think in terms of pressure, volume, and work. So if you remember that work is equal to negative pressure times delta volume. Okay. No work has been done. The pressure in this is a vacuum. Okay, so this is a vacuum system that we're looking at. So that means our pressure is 0, so our work is 0. No work is done in this system. And then if you remember the first law of thermodynamics, which is delta U for internal energy is equal to Q plus W. And there's no heat being transferred here, so Q is 0, and there's no work being done. So our change in energy, our delta U, is still 0. So there's no change in energy. There's no work by the system, but this still has the spontaneity occurring where this gas is moving to fill up that empty space such that you have this overall uniform distribution. Another example is if you have two objects that are at different temperatures that are placed in contact with each other. If you remember, heat flows from hot to cold, but there's no overall change in energy. Okay, they do this until they are equal in temperature. But yeah, there's no overall change because the heat gained by the cooler object is equal to the heat lost by the warmer object, so the overall change is 0. So both these examples we're looking at were spontaneous processes that resulted in a more uniform distribution of either matter or energy. The first one being matter with the gas, the second being energy with heat. So let's look at an example. We want to describe how matter is redistributed when the following processes take place. The first is a solid subliming. So if you remember, sublimation is when you go from a solid to a gas without it forming a liquid first. So you have a much greater dispersal of matter because now you go from molecules having a small volume. Whoops. I don't know why that happened. So we go from a small volume to a large volume when this happens because when we're forming this gas, those molecules take up the entire space that they're in. So a solid has a set volume, if you remember from chapter 2 on matter, whereas gases don't have a set volume. They take on the volume of their container. Okay, so now in B, we're told a gas is condensing. So this is where we go from a gas to a liquid. So now we are going from a large volume to a smaller volume because those molecules are getting closer together. They're slowing down, going from the gas to a volume. So remember, liquids have a set volume. They take the shape of their container, but they have a set volume. Okay, and then C, a drop of food coloring added to a glass of water forms a solution with uniform color. So this is diffusion. So what's happening is the dye is dispersing throughout your liquid until eventually you have a uniform dispersal of matter. And you wind up with a system with a uniform single dye concentration throughout. So if you take a drop of food coloring and you put it in a glass of water, it might take it a bit, but eventually it'll get to a point where the entire glass is the same color and that dye is spread throughout. Hello, laptop. Okay, that was weird. My laptop did not want to switch slides. Okay, and then these are just pictures kind of showing those processes happening.